you go. Okay, so 5.2 is about a thing called sigma notation. Sigma notation is a thing we use to find sums. When you had trig, it's likely we did some stuff with sigma notation. I'm never positive. You might remember more than me. You remember seeing that you saying, yeah, usually that's the thing we get to. The end of the year in trig is different every year. It's sort of scrambled by count of days and what we have left. But I think you've seen this before, and you think so too. People watching the videos, maybe that's true, maybe it's not, but it's usually true. But sigma notation is just a way that we can find sums. So the way I would read this is the sum as k goes from 1 to 3 of k squared. Did either of you remember what it is they were expecting you to do with that?
Plug in 1, 2, 3.
Plug in 1, 2, and 3 into k squared, and then since we're finding sums, we want to add it. So you plug in 1, you get out 1. Plus, plug in 2,
4,
plus, plug in 3,
9.
9. And then it depends on what section of the homework it is and what their style is and what the book is. Some books are just happy with that. Other books might want you to actually go through and add these and come up with 14. I don't know. Check the back of the book on number 1, see what they're doing. You know, if they're at it, go ahead and add it. If they're not, go ahead and don't. Doesn't matter to me. Do you remember what this causes to happen? Because if we did sigmas, you would have encountered questions that had a thing like this in there. Remember what impact that'll do?
Odd powers keep the sign, like, and then even powers changes.
Yeah, it's going to alternate signs. It's going to go negative, positive, negative, positive, negative, positive, back and forth. Whether that's negative 1 in there to a k, or whether they do k plus 1 or k minus 1 or anything like that. If negative 1's in parentheses to a variable power, it's just going to make the signs alternate. Let's do the number part first and do the sign part second. So if we plug in 1, 2, and 3 into that again, we'd get out.
-1.
Let's not worry about signs yet, but the base numbers would be 1, 2, 3.
Okay.
Then if we think about -1 to the first, -1 to the first would be negative. Then you don't have to think about the other ones, they just alternate. If you want to think about them, you can. This 2 goes in, and even power makes things positive. Then the 3, and odd power makes them negative. But you don't have to, like, think it out. Just get the first side, and then make it. If I did k plus 1, that would change this game a little bit, because now when we plug in the 1, 1 plus 1 is 2, and even power makes this positive. Then they're going to alternate, negative, positive. You could think them all through if you want to. I mean, when you plug in 2, 2 plus 1 is 3, 3 is odd powers get you negatives. Put in the 3, 3 plus 1 is 4, which is even powers get you positives. You can think them out on one at a time. But this -1 to a power business just makes the signs alternate. So when we go into rewind mode over here in a second, that's got to have some answer that has to do with -1 in parentheses doing something, because I made the signs alternate. This one, what do you think?
27.
7,
64.
4,
125.
alternate. You'll probably find the questions very easy when moving in that direction. When they give you the formula and you just have to do the plug-ins, I don't think you're going to find that to be a real challenge. Question about that. The only way they could make this a challenge, and they don't, is if they wanted to be really mean and go like 3 to 50. Right? That's just mean. Okay? They made it long, but they can't really make it hard. They won't make it long. There's no 3 to 50s. Question about that? What you'll find more mentally challenging, and you're going to maybe find yourself sometimes skipping one and moving on and coming back, is when they give you a adding problem and want you to come up with the formula. The nice thing about it is, one nice thing about it, or maybe it's a mixed thing about it actually, is there's not really one right answer all the time. There could be 2 of you with 2 different answers. my answer could be a third different answer. There's not always like, this is the only way to do this. So sometimes that's good, but sometimes that's like annoying, because I don't know, if you get in conversations with other people and you did it 2 different ways, you're both maybe right, it could be okay, that's a little frustrating. The other thing that's a little frustrating about this sometimes is, you just have to have the right creative idea. And if you don't have the right creative idea, you could spend 1 second like, I got it. Or you could spend an hour just like staring at it thinking, I don't see the pattern for this. So I'm a big fan on this homework of if you start to like get frustrated, just skip it and move on. And sometimes a fresh set of eyes on the same problem an hour later or a day later, you're like, oh, why did I see that yesterday? It happened. But I'd look for commonalities. Okay, so the first thing I'd look for in this, I'd see commonalities of, these all have 1s on top, so that's not really super earth-shaking. And then you probably see a pattern there on the bottom that's just going 2, 3, 4, 5. So how can you make it go 2, 3, 4, 5?
Go from 2 to 5.
Yeah, take your K's from 2 to 5 and call this
X. Okay.
Okay. That's perfectly fine. That's the most likely answer that I would get. I have sometimes people that get a little bit rigid about this in their approach, and they always want to start with 1. And that's okay. If you wanted to start with 1 and call this 1, 2, 3, 4, sometimes it even helps to number them off. 1, 2, 3, 4. Our K's would run from 1 to 4. If this is what's called K, how would we adjust all of our K's to make what we're looking at K plus 1? That's just as good of an answer. Okay, back to you. If I wanted to be absurd, I could run my K's consecutively from 100 to 103. There's still a 1 on the top, but if I'm going to go from the number I chose ridiculously to these, I would have to, at each level, subtract 98. That's just as right. It's kind of weird to like choose that, but all of those answers are right. Does that make sense? I'll just let that hang, but I would never have put that. This one, I don't see any great commonality. So if I don't see a great commonality, I might just pick my K's. I feel like on this one, my K's should probably run from 2 to 4. And my answer needs to have a K, just like the one I did a second ago over here had a K. But we talked that when we did that same one, we've noticed that in this feature problem, we were going to have those alternating signs. So we need to go -1 in parentheses to some sort of a power, but that it's like a 50-50 shot that I just want a basic K there. We'll have to check this by plugging in. If I plug in the 2, -1 to an even would turn out positive, and I want to turn out negative. So this isn't right, and there's 2 ways that we can adjust any even into an odd. We could do an add one. We could also just as well do a subtract one. But that'll do it. We'd always, to alternate signs, you'd either have this or its friend to subtract, or this I threw in the +1. I didn't want the +1 originally, did I? So either -1 to the K or -1 to the K, either +1 or minus.
How come you can't make the K negative instead of adding a +1?
You could do that too. That would also work.
Okay.
I always just do that. Personally, my approach is always put in -1 and put a K on it, and then test it. And if it's wrong, I personally just add 1. But you can make that your other personal approach. That's fine. This, I don't see any obvious K's. I don't see any super obvious commonalities the way I had the 1 on top. But these numbers all do have a commonality. Well, anybody sense a pattern to this at all?
2 to the X.
It's 2 to a power. Okay? If you look at it and you see that it's going to multiply 2, multiply 2, multiply 2, multiply 2. If you're going to repeatedly multiply 2, that's why humans invented powers. Humans invented powers to do 2 times 2 times 2 times 2 times 2 times 2 kind of stuff. So this absolutely has to have something to do with 2 to a power. then there's options of how you structure that, but you can't do this without 2 to a power, that is for sure. These happen to all be powers of 2. This is 2 to the 2, this is 2 to the 3, this is 2 to the 4, this is 2 to the 5. So the simplest thing to do is to call the power K and run the K's from 2 to 5, but that's not exclusively the only answer. What if I did the same problem, but 40 plus 80 plus 160 plus 320? Now those aren't all perfect powers of 2s, but it does still have to involve a power of 2, because we're still going times 2 times 2 times 2 times 2, lots of times 2 times 2 times 2s. How can we make that adjustment now? What did I do to jump from there to there?
Multiply 10.
Multiply 10, we can go now. But if we started from scratch on this one, it would have been harder to like figure that out. But you would have had to figure out something's going on in powers of 2 and try to build from there. This one, we're going to add 2, add 2, add 2. 2 plus 2 plus 2 plus 2 plus 2, what the humans invent to do repetitive addition kind of problems. Multiplication. This absolutely has to have something to do with 2 times stuff. It's absolutely 2 times stuff. Then the question just becomes, what do you want to run your k's from? And you can't go to this and do k to be a half. Okay? The k's have to be whole numbers. So we need some sort of whole number to get us into that neighborhood. What do you think for a k?
We go 0 to 4.
We could go 0. We could also have gone 1. If we do 2 times 0, well, and then let's figure out what our top limit is. From 0 to who? 3. Use your fingers if you need to. 0, 1, 2, 3. Or 1, 2, 3, 4. But if you're going to go 2 times 0, 2 times 1, 2 times 2, 2 times 3, you're in the neighborhood, but you always, to fix it, need to add. If you did 2 times 1, 2 times 2, 2 times 3, 2 times 4, you're always in the neighborhood. Correctly. If you wanted to do something stupid, just to be creative, you know, start with any number you want. 10, 11, 12, 13. It's still 2 times k. With 2 times 10, I'm high by 19 now. 2 times 11, 2 times 12, 2 times 13, I'm always going to be high by 19. That's just as good of an answer, but it's sort of a dumb way, a hard way to like come up with it. That's where the homework's going to slow you down, is the second section. The first section is going to flow real smoothly. The second section, you're going to have some moments that you're like, oh, I'll come back to that. It's just going to happen. Question there. Then there's the easiest group of all. They'll tell you, we have a sigma kind of problem worked out. We're going to call it A. We worked out the answer is going to be 2. We're running from 1 to whatever. We'll keep the 1 to whatever the same, and we'll do another formula. We'll call that B. And we worked that out for you, and that result would have been 3. Then we'll come back at you and ask you a question. We have to keep these limits the same, from 1 to n still. What would A's plus B's be? 5. Because all you need to do is use the 2 in A slot and the 3 in B slot. That's going to be the easiest group of this homework by far. If they want 3 of the A's plus a 6, you would simply go with 12. There will be a couple of those. That's going to be the greatest group of the page. Question over here before I stroll over there? Okay. If I go back to this one just for a second on my walk, in the section where you're going to actually make the list and add, there are no ridiculous long ones. If they decided to go from 1 to 30, you'd be mad. And I'm going to stroll over there, and there's some formulas that can help us do different common sigma problems when these numbers start to get out of control, or even when they don't. Okay, but 1 to 30, you don't want to do that way. Well, we got a shortcut coming over here. So here I go, stroll to the left. And here is the birth of a great item that you might be familiar with from other people in calculus other years, and today is the day that it's born. It is the Calculus CCA note card. A Calculus CCA note card becomes available to you. You have to buy your own note card. You can fill the front, you can fill the back. I would leave some room to grow on. I would not like get this card and fill it up completely today. I'd leave some room to grow. But put on there these 4 formulas for sure for this chapter's purposes. And anything else you have found yourself over the year having to look up. If you're not great at the trig chart, write the trig chart on it. If you're great at the trig chart, don't waste your time putting the trig chart on it. If you do the trig chart and sometimes you forget about this, write that on there. If you can't remember that the derivative of sine is positive cosine, and the derivative of cosine is negative sine, if that jams you up, write that on your card. If you forget the derivative of secant, what that is that secant tangent or is that secant squared? Something secant tangent, something secant squared. Which one is which in the trig? If you get that crossed up, write that on your card. You can't remember area of a circle, volume of a sphere, write that stuff on your card. Okay? Anything you find yourself having to look up when you do your homework, when you look it up, write that on your card. And when you go to take a quiz, you're good. When you go to do your review sheets, it's already there. If you have to look it up in the homework, look it up. If you know there's things from the past that you've had to be looking up, think back through your memory bank, and those are all good things, the trig derivatives, the trig terms, and stuff like that. Because these, no human needs to memorize these. Okay? But if you don't have these memorized, you can't do them. So I'm not going to make you memorize those. We need some sort of cheat sheet for that. And while we're doing it, just make yourself the ultimate cheat sheet of that. What you can't do on your card is like example problems. So you can't be like, you know, if I just wrote really little, I could fit this whole practice quiz basically on this card and make every quiz like an open notes quiz by having all these like sample problems, and then all you have to do is mimic the numbers in like tiny miniature form somehow. That's not what we're doing. This is for reference information. It's like things that you could memorize but don't want to. Does that make sense? Where the line is on that. So here's the 4 formulas to start building your card and to do the last section of homework. And this will be like the first section. This won't be done. This is just plugging stuff in. If they ask you to do a sigma problem with a constant, like 8, 10, a million, pi, 3/5, any kind of just a number, you take the upper limit times the number. So if I went from k goes from 1 to 100 of 7, it's just 100 times 7. Which makes sense. If I told you, add up 100 sevens, you wouldn't add up 100 sevens, you would do 100 times 7. If I ask you to add up from 1 to whatever a bunch of k's, we're going to try to add up 1, 2, 3, 4, 5, 6, however high it would go. We want to add up all the numbers from 1 to 100. The way we can do that is take the upper limit times the upper limit plus 1 and divide by 2. The way that formula runs. If we did this kind of stuff in trig, I probably told you the story about Gauss. Gauss was like a young math whippersnapper that kept his teacher on his toes, and the teacher would get sort of annoyed by Gauss, had trouble keeping Gauss busy. So one day the teacher said to Gauss, just get out of my way, go add up the numbers from 1 to 100. And Gauss went, okay, I'll go add up the numbers from 1 to 100. It's 5,050, teacher. And teacher was like, what in the world? And Gauss figured out, if you did the numbers 1 to 100, like counting up, let's say, to 50, and then reverse course, 51, 52, 53, 97, 98, 99, 100. He figured out if you paired off biggest and littlest, what helps if I do 99? I'm gonna go there with that one. If you pair off first and last, next two, next two, next two, all the way to the middle two, every pair of numbers will add up to 101. And then there's like 50 of them. And that's essentially what this formula would do. If we were adding up 100 numbers, 100 plus 1 is what each pair does, and 100 divided by 2 tells you how many pairs there are. There's 50 pairs, because 100 divided by 2 to pair them up, and the sum of each is 100 plus 1. Like, he figured that out as like a little kid, 8, 10, something like that. Like, he didn't figure out the formula, but he on his brief little exchange with his teacher was able to she thought that was going to keep him busy by him going 1, 2, 3, just having to write out all the numbers from 1 to 100 like a writing assignment and add them was going to take him a while, but he didn't even begin to do it that way. K squared, we just need to work the upper limit and just plug it in. Upper limit plus 1, 2 times the upper limit plus 1, divide by 6, and it always will divide to be an even number for some, it'll divide evenly for some reason. That who knows why, I'm sure there's a reason why, but it will. The cubed formula gets more complicated. I'm sure somewhere there's a fourth power problem, but the book doesn't do it, so I don't do it. But you could Google that and find probably these sigma formulas for any power, but the homework will stick to numbers, k's, k squared, k cubes. So I've had some people argue with me historically that they don't want to memorize the formulas, they don't want to write them on the card, they don't want to be bothered with the formulas. What they want to do is what we did here, which is plug in 1, get an answer, plug in 2, get an answer, plug in 3, get an answer, plug in 4, get an answer. That's what they want to do, and add them up, and that's the way they're going to do it. And I've had some people with snotty attitudes about that. So some of the tests you'll see, I'll make it change, and I'll show you the change in a second. But if we want to do these formulas, the k squared formula, we just look to this. Only the upper limit matters, so I go 4 times 5 times 9 divide 6 minus 3 times, then use the k formula with 4. If we use the k formula with 4, that's 4 times 5 divide 2, and then we'll map that up in a second. Question about setting up. I'm not a big calculator fan, which you know. I'll more math this in my mind. If you need to just calculator do it, just calculator do it. But I would go, personally, 4 times 9 is 36. 36 can divide by 6 to get 6. Times 5, that's 30. I don't feel the need to do a calculator there. 2 can go into 4 twice. 2 times 5 is 10, times 3 is 30. 30 minus 30 is 0. If you can do stuff like that, do stuff like that. Keep your mind sharp. If you want to just blind plug it into the machine, go for it. But question about that. So again, here's the argument that I've had with people where they're like, I don't want to do that. I just want to plug in 1, I want to plug in 2, I want to plug in 3, I want to plug in 4, I want to add them up. That's easier for me, that's what I'm going to do. I think that's harder, personally, already. But just to stomp out that attitude, you'll notice some of the quizzes, I go like this. Okay, so how hard is it for people using the formulas to do 40 instead of 4, and then 41 instead of 5? That's not a problem. But people that want to be snotty about this, they would then have to plug in 1, 2, 3, 4 out to 40. So just don't, you're not snotty attitude kids, generally speaking, but just copy the, just copy the, or maybe ever. Okay, but copy the formulas on your cards and just use them. Don't give me a bad time about it. But I've had that argument. So when you see some of the sheets, if you're like, why do you pick 400? I mean, if you're using the formulas, it's just a number. But if you're actually trying to plug them in because people argued with me, then that's no fun. Question about the thing there? So cubed formula, how's the cubed formula going to run?
4 times 5.
And then the 6 falls into the top level of, it's just a number. 24. 4 times 6 if you prefer. Mathing this, I'd go 2 into 4 goes 2 times 5 squared plus the 24. Well, yeah, no, I thought it was a good trick, but I've had some argumentative people over the years. Not a lot, but you do stuff with teenagers long enough, you meet some argumentative people. You do stuff with adults long enough, you meet some argumentative. There's argumentative people in every age bracket. I shouldn't be prejudiced against teenagers on the argumentative zone. There's plenty of people of all ages that'll be argumentative when you're just trying to like give them another way to do something. I don't like different ways to do things. Whatever, I don't. Question my stuff. Homework off of this is syllabus will know. We're in the 200 somewhere. 292 is where this lives from 1 to 28. The first like 10 involve plugging in. And some of them are which of these things is not like the others games. Like you just plug them in to see if they're the same or different. 11 to 16 is the zone that's going to make you sweat a little bit. You're going to have to be a little creative and hope for that right inspiration at the right moment. 17, 18 are the ridiculously easy ones. And then 19 to 28 is based off of the formulas and note card type information. That's a wrap on